All right, we're going to get started with graphing. Okay, so this is the one major question from this week. The other one was about change of base, which I think is a little bit more straightforward. But graphing is a little bit tricky, so let's talk about it. Okay, so going through, this is problem number one on the assignment. I think you guys had to do one, two, and three. So we'll do one together, and hopefully that'll allow you to do two and three. Okay, so for problem number one, the first part should be fairly straightforward. We've talked about parent functions all year, but just to kind of recap what a parent function is, we said if you remove all of the transformations essentially, so that would be any addition or subtraction, right? That's your C and D values, which we're going to talk about more of that down here. But you can see that I have a value inside of the log that's a C value, and I have a value outside of the log that is being added or subtracted. That's a D value, right? So if I remove those, okay, and then any multiplication or division, right? So if I had, for example, like a little 2 sitting here, it said 2x minus 1, that would be multiplying by the x. Also, if I had a number outside of the log saying 2 times the log, that would be an a value and a b value, right? So if I take away all of that stuff, which for us is just this minus 1 and this minus 5, what I'm left with is, and I'm just going to use a y instead of a g of x, y equals the log base 6 of x, right? This is the parent function, okay? And we said that in the video that this is related to exponentials in a way. It's actually the inverse of an exponential. So before we talk about the rest of these questions here, I just wanted to kind of quickly recap what an exponential would look like. Okay, if I were to draw a very terrible graph like this, we said exponential, the parent function of an exponential basically looks like this. It's along the x-axis, right, kind of very flat, okay, because there's an asymptote right on the x-axis at y equals 0, okay? And it's going to then slowly turn, okay, and head up and kind of look like this. Okay, so this is what an exponential looks like. Okay, so we said that since logs are the inverse of an exponential, that what we're going to see is all of the features of this exponential are going to be switched, right? So what we typically would say if we were just talking about this generic graph, if this one had a this exponential, which we'll just make something that we'll call this y equals 2 to the x, okay? If we said that this was what we just graphed, okay, and it looks something like this, okay, that the asymptote for this would be y equals 0, okay, and we were to say it would go through the x-intercept or the y-intercept at 0, 1, right? These are the questions that you answered when you did exponentials. If I were to invert this, which means turn it into a log, it would look something like this: log base 2 of x is equal to y. That would be kind of switching all of this information. So instead of it being about y equals 0, we could say that it has an asymptote at x equals 0, right? And instead of the y-intercept being at 0, 1, we could say that the intercept is at 1, 0, right? Inverses are just x and y being switched, so we're just going to take all the information and switch it. The domain of this exponential is all real numbers, okay? Okay, so that's the domain, okay? And the range is y is greater than 0. Okay, so this is kind of the typical information that you would see, with the exception of this, right, around an exponential. A log function is exactly the same, except every x and y piece of information is flipped. So instead of this being, if I were to talk about logs, a generic log, not this specific problem yet, we would say that it has an asymptote at x equals 0, right? So if I were to graph that, since I can't draw straight lines very well, I'm going to use my graphing tool, or my line tool. Give me 1 second. Okay, so I'm going to grab a dotted line. We'll make it red. Okay. So instead of there being a horizontal line at y equals 0, there's going to be a vertical line at x equals 0. Okay. And this is my asymptote for the parent function. Okay. Instead of the y-intercept being at 0, 1, there's going to be an x-intercept at 1, 0. Okay. Instead of the domain being all real numbers, we're going to say that the range is all real numbers. So I'm actually just going to put that here. Okay, this is true of every log function, that the range is all real numbers. Okay, and that's because it's the inverse of this exponential. Okay, we're going to say that the domain is x is greater than 0. Okay, instead of y, right? Because we flipped it, right? And you can see that I have this dotted line here. We're going to have this graph that kind of goes flat along the negatives, right? Remember, we went like flat along the negative here and then turned. So we're going to do the same thing, flat along the negative y, okay? again, just pretend I can draw straight lines. That's really bad. So we're going to try that again. Okay, so we're going to go like this. Okay, and it's kind of riding right along this axis. Okay, and then it's going to turn, hit that 1, 0, and kind of go out like that, right? So again, just ignore my terrible line drawing, right? But you can see that it's kind of going up along the axis, turning, and then heading straight out towards the positive x values, right, all the way to the end. So there's an asymptote at x equals 0, okay? And the x-intercept is 1, 0, right? We can do all that, okay? And then we'll describe all the transformations. So this is kind of what all of our log functions are going to look like. Almost the same as an exponential, but it's flipped over, right? And it's kind of heading to the right and down instead of heading to the left and up, okay? So that's kind of the general look of a log function. So now we have to apply this to this particular problem. So here's what we're going to say for this particular problem. I'm going to erase all this, and we're going to talk about this problem, okay? We're going to make a little XY table, okay? But we have to be careful, okay? Let me get my eraser. Okay, so here's the deal, okay? Couple things, okay? First thing is that log functions are not allowed to have a negative number or 0 inside. And I'm actually going to grab my calculator to show you, okay? If I get my calculator out, and here's my log button, it doesn't matter what the base is. And if I hit 0, which is currently what's on here, and I hit the log button, it gives me an error and says invalid input, okay? I can't do that. If I plugged in a 2 with a negative sign, right, so -2, and then I hit the log button, I get the same error message. If I plugged in a positive number like 5 and hit the log button, it's like, cool, I can do that, okay? So the number that's inside of here is not allowed to be 0, and it's not allowed to be negative. And so what that means for us, for the domain, is that, and this, I'm going to kind of start it here. We'll do transformations at the bottom, okay? We're going to say that the domain, okay, the expression in here, which is x minus 1, has to be greater than 0. It's not allowed to be equal to 0. It's not allowed to be less than 0. And then if I solve this, I'm going to say that that means that x has to be greater than 1, okay? So what that means is when I create my table of values, I cannot plug in 1, and I cannot plug in things smaller than 1. I can only plug in things that are bigger than 1, okay? So I'm going to pick values. So I'm going to say x, y. Here's my table, okay? And I'm going to plug in, I'm going to start by plugging in the first value that I can do, which is a 2, okay? And then I'm going to plug in the next value, which is a 3, okay? And let's just see what happens when we plug these in before we do anything else. So if I plug in a 2, here's what I get, okay? It's going to say the log base 6 of 2 minus 1, okay, minus 5, okay? So 2 minus 1 is 1. This is going to become the log base 6 of 1 minus 5, okay? Okay, so we have to think now, okay? What is the log base 6 of 1? Okay, you could do your change of base formula if you wanted to. We learned about that last time, so we'll do a little bit of that in a second. Okay, but for this one, we can actually just think about it. We're actually saying 6 raised to some power is equal to 1, okay? And if you remember your exponent rules, 6 raised to the 0 power, anything raised to the 0 power is 1. So this is actually a 0, okay? Minus 5, well, that means that's -5, okay? So now I'm going to plug in a 3. If I plug in a 3, this is going to become 3 minus 1, which is 2, okay? And now here things get a little trickier. This is saying 6 to some power is 2. Oh, I don't know what that is, right? So that's a little tougher. So what we have is the change of base formula from last time, which said if you do the log base 6 of 2, that what that really is going to be is if you do the log of 6 over the log of 2, right? Remember, these are base 10s, okay? That'll allow me to use my calculator, right? So I can actually calculate the log base 6 of 2 by grabbing my calculator, and I'm going to type in a 6, hit the log button, and I get this big ugly number, okay? I'm going to divide that by, I'm going to hit 2 and then hit the log button, that ugly number, and I get about 2.5, okay? So let's see if that makes sense. It actually doesn't make sense. Oh, I did it backwards. Let's try that again. 2 should be on top. It's the log of the number over the log of the base. So log, okay, so just to kind of give you a little insight, I saw this answer, and basically what this is saying is that if I raise 6 to the second power, I would get a 2, right? And that doesn't make sense. It should be like 36, right? So that number didn't make any sense. So that's what made me go back and remember that my my formula was upside down. I want to do the log of 2, okay, divided by the log of 6, okay? And that is 0.38. That makes a whole lot more sense, right? So if I raise 6 to the 0.38 power, I'll get a 2, which is smaller, okay? So I'm going to take that, and then my problem says once you have that answer, subtract 5. So I'm going to subtract 5, okay? And so that's going to give me about a negative 4.6. So I know when I plugged in a 3, I got a negative 4.6, okay? So let's graph these and see where we're at. 2 goes down to negative 5. Here it is. Okay, 3 goes down to negative 4.6, which is like right there. Okay, so here's what I want to start pointing out. Our previous problem, the graph kind of rode right along here, okay, and then turned up here and went this way. Okay, and I'm starting to see that turn right here. Right, it looks like my graph is going to kind of be like this. Okay, that is because, and let's talk about some transformations. This minus 5 shifted my entire graph down by 5 units. Right, so I'm expecting instead of seeing it up here. See, everything shifted down by 5, and it's going to be down here somewhere. This minus 1 is doing the same thing, okay, and it's shifting the asymptote over 1, right? So my domain, we already said, is x is greater than 1, okay? And that's because I have an asymptote at x equals 1, okay? So I'm actually going to take this dotted line, and I'm going to shift it over right there, okay? So what I know, based on this transformation, this c value, is that my graph is going to kind of ride right along this dotted line at x equals 1, and then it's going to turn and head up, okay? So I want to kind of make my graph look a little nicer, right? And I'm going to pick 2 more values just so we have a nicer looking graph. I can't really get a good look at my graph with just 2 points, okay? So here's what I'm going to be picky about. I'm going to purposefully pick an x value that I know is going to work out nice, and here's the one I'm going to pick. I'm going to pick a 7, okay? And here's why I'm going to pick 7, okay? If I do 7 minus 1, right, in the original problem, I get a 6. And the log base 6 of 6 is something I can do in my head without a calculator. It's saying 6 to some power is equal to 6. Well, 6 to the first power is equal to 6, right? So I can make this log base 6 of 6, which is a 1, okay? 1 minus 5 is negative 4. Okay, so if I go all the way over to 7, I can go down to negative 4, okay, right there, and I know that's where my graph is. So I know this is kind of flatten out pretty quick, okay, and then I know it's going to turn down this way, so I'm not going to bother plugging in like a decimal here. So I'm going to graph this just with these 3 points, okay, and it's going to go like this, okay, and it's going to turn, and it's going to go down as well, and it's going to, let's make that turn look a little better. It's going to go this way and turn. And it's going to go down like that, right? So that's my graph. That's pretty accurate looking graph. It looks a lot like my original one, but it's been transformed. It moved to the right by 1, and it moved down by 5. Those are the transformations that I described based on my c value and my d value. So I'm going to say for my described transformations, okay, it's going to go to the right by 1, okay, and that's because of a c value that's equal to 1, okay, and it's going to go down by 5, okay, and that's because of a d value that's equal to negative 5, okay? So these are my 2 transformations, okay? The last thing that we have to talk about is this x-intercept, okay? So you can see that the x-intercept would be, where does this cross the x-axis? Okay, it doesn't look like it does, okay? But this is kind of very, very slowly increasing, right? It's like way over here at like 12, it might only be up at like, you know, still negative 4 point or 3 point something, right? So it's taking its time going up. So what I'm expecting is that it will eventually cross the x-axis, but at some very big number, okay? Because it's going to take a long time to get up there. We're going to calculate what that value is. So I'm going to give myself some space, and we'll move down a little bit, okay? So here's what I know. Every x-intercept is some x value with a y value of 0, right? 1, 0, 2, 0, 3, 0, 4, 0. I know that the y value is always 0. So what I'm going to do is I'm going to take this original equation, and I'm going to make g of x, which remember that's the same as y, I'm going to make that 0. So I'm going to say I know that for every x-intercept that the x or the g of x or the y value is 0. I'm going to bring everything else down, log base 6 of x minus 1 minus 5, okay? So we're going to solve this equation. We're going to try to get x alone, and then we'll know what the x-intercept is, okay? So to do this, here's what we said we did. Try to isolate the log. So I'm going to add this 5 over, okay? So let's say 5 equals the log base 6 of x minus 1, okay? And then once the log is alone, that was all we had to do. We're going to convert this into an exponential. So I have a base of 6, an exponent of 5, an answer of x minus 1. So it's going to say 6 to the 5th power is equal to x minus 1. Okay? So let's grab our calculator. We have to do 6 to the 5th power. 6, x to the y5, and I get 7,776, okay? 7776 equals x minus 1, okay? And then if I add that 1 to the other side, I get 7777, okay? This, as big as it is the x-intercept. We're going to have an x-intercept at 7,777, comma, 0, okay? And I know that sounds a little absurd, but if you, again, take a look at how slowly this is. When I went from 2 to 3, it only went up by like 0.6. I'm sorry, from 3 to 7. Right? I went from 3 all the way up to 7, and that only increased my y value by 0.6. Right? And it's actually going to slow down a little bit. It's taking its time getting up there, so it's actually going to take until it gets all the way to 7,000 on the x-axis for you to get up to the x, to actually touch the x-axis. So it takes a really long time. Okay, so that's kind of the summary of everything that's going on. The parent function is strip away the transformations, in this case just the c and the d value. The domain you can calculate by setting the inside of the log greater than 0, right, and then solving it. The range will always be all real numbers. Okay, the asymptote will always be related to this c value, because that basically is telling us what's going to happen to this dotted line. It was at 0, we moved it to the right by 1, that's going to change that. The x-intercept, we just saw the calculation, right? And the transformations, again, are based on what's happening with your mostly c and d values. The a and the b might cause a reflection or something to happen, but I don't believe you guys have any problems that will do that, okay? So if there are any other questions that you want me to go over, let me just make sure I don't have any. Okay. Okay. So yeah, it doesn't look like I have anything else. So I'm gonna hit the stop button, okay, and stop streaming. But if you have any other questions, please feel free to email me, and I can help you via email. There will be another live stream scheduled for next week on Wednesday and Friday, so you can wrap up the last 2 assignments, which are about E and ln, the natural log. So let me know if you have any questions about those. Otherwise, have a good weekend.